Hey guys, this is the last section in first semester calculus math 30, the substitution method. This is a method for finding integrals. And what you're going to find in Calc 2, Math 31, is that finding integrals, in other words, in a sense going backwards from what we've been doing finding derivatives, is a lot more challenging. So this is our first method for helping us find integrals. So let me start out with what is the substitution method. And if you remember, this is essentially the chain rule in reverse. So the idea is that if we can take some function that's plugged into another function, and when we take that derivative, we still have the derivative of that function, we're going to substitute that with what we call a u function. So this is confusing to say it that way, so it will be easier to show you what we're doing. But the idea is that we're letting u equal some g of x, and the g of x is something that we see in our function that we're trying to integrate. And then we also have g prime of x in the function we're trying to integrate. And if we see that, then we can use this u substitution method. So how does that look in practice? Well, let me do one like this. Now we know, without using a u substitution, that the integral of this polynomial function is simply, well, I need to integrate this first term, 2x, bring the power up 1, and then divide by the new power. So those 2's cancel, and then we have a 5, minus 5x rather. And then of course you want that plus c because we don't know what constant was there before we took the derivative. So this is just x squared minus 5x plus some constant. Alright, but if we were to use the u substitution method on this, so we're trying to integrate 2x minus 5 dx, dx, jumping the gun there, what we would do is we'd say, okay, let u equal, and here we have some choices. I could let u equal 2x. I could let it equal that whole thing. What's important is that when we take the derivative of u, and I'm just going to call this du, and I'll put my dx on the other side. That's what we do in integration. So the derivative of u is 2, and then I'll put a dx. Now, we don't have, so what we're looking for is a 2 dx in our original function. But we don't have a 2 dx, we only have dx. So I can give myself a 2 dx. Whenever you need that constant, you can always just throw it in there, as long as you pay for that somewhere else. So I just multiply by 1/2 and a 2. And there I have my 2 dx. Okay, so what I'm integrating now is, well, I'm saying u is 2x minus 5, so I'm going to call that u, and this 2 dx, that is my du. Alright, now this becomes simply, I'm integrating, so simply u squared over 2 plus c. Okay. Well, now if I put what I know, and actually let me go ahead and distribute this 1/2 in. So that's going to give me u squared over 4 plus, and now this is the interesting thing that's going to come up a lot in Calc 2. when we multiply 1/2 times our constant, we still have a constant. So I'm just going to call that plus c still. And technically, you know, you might call this C1 and C2, but we really don't care. We just need to know that there's a plus a constant at the end. Okay, so if I were to plug u back in, this is what we'd have. Alright, so I just plugged what I had for u back in to u. I've got it squared. So simplifying it, hopefully we end up with the same thing that we have in the original integration. So let's see, this is going to give me minus 20x, and then finally plus 25 it looks like. And I'll put each of these over 4. And again, I'm going to use that trick when I add a constant to a constant. I'm just going to get a constant. So this is going to become my new c. And indeed, we have x squared minus 5x plus some constant, which is what we had up here. X squared minus 5x plus a constant. So why would we use the u substitution? It looks like it's making things more complicated, but I wouldn't, to be honest, use the u substitution on this. This was just for illustration. I would use a u substitution on this next one. So we have e to the power 8x minus 2 dx. I'm going to use the u substitution, and a lot of times, just fair warning, when you're doing a u substitution, you might try, so I'm picking 8x minus 2, you might try a u, and then you find out that you don't have the du that you need. Du is going to be, well, I'm just taking the derivative of this, so that's just 8 dx. Now I don't have an 8 dx, but I'm going to use that trick again because it's just a constant. Multiply by 8 and divide by 8. Alright, so what we're integrating then is e to the u du, but I have that 1/8 out front. The 8 dx is my du. Let me give you another way to think about that constant. So this is the way a lot of people prefer. I could divide both sides by 8. So that leaves me with 1/8. Put that down in the white area here. 1/8 du equals dx. And now I'm just substituting my x, dx, with a 1/8 du. And that 1/8 I can bring out. So either way, I'm going to have a 1/8 out here. And I'm integrating e to the 8x minus 2, which I'm calling u. And then my dx was the 1/8 du. And we know how to integrate e to the u. That is just e to the u. And so, plugging u back in, or substituting u back in, I find that the integral of e to the 8x minus 2 is just 1/8 e to the 8x minus 2, but of course plus c. And if you ever want to check that you've got the right integral, just take the derivative of what you've got, of what your answer is, and see that you end up with what you started with. Okay, so here, let me try u equals 3x minus 11, and du is going to equal, well, just take the derivative of this, 3 dx. So again, we just have that constant. I'll use the trick I used last time, just divide both sides by 3. So I have 1/3 du equals dx. And so let me substitute what I know for what I chose for u. That's square root of u, and dx is just 1/3 du. All right, and now we know how to integrate u to the 1/2. So let me pull that 1/3 out first. And u to the 1/2 is u to the 3/2 divided by 3/2 plus c. And now if I simplify that 3/2 on the bottom, I'm going to get 2/9. Let's call this, how about plugging back in what I chose for u, 3x minus 11 to the 3/2. All right, how about let's throw a trig function in here. Let's try u equals 10x minus 3. du is 10 dx, so 1/10 du is what we're going to substitute in for dx. Alright, so plugging all that in, I'm going to have a 1/10. I'm moving that 1/10 out front already just because I know I can. It's a constant, multiple. So sine of u du. And I know what the integral of sine is. Be careful here. Is negative cosine of u plus a constant. Oh, and look, I missed my constant in the last one. My final answer. All right, so switch colors here, see if that works. That looks a little weird. Green. It's a little better. Okay, equals. Now I'm just plugging in what I know for u. What I chose for u rather. Okay, so I brought the negative out. I'm gonna have negative 1/10 cosine of 10x minus 3 plus c. And that's my integral. Okay, let's make things a little more interesting. This time, I'm not going to get for when I do my du, I'm not going to get just a constant times dx. So for example, let me come down here a little bit, and I'll use my sheet. If I'm integrating 8x cosine of 4x squared plus 3 dx, well, let's let u be, I'm going to let it be this inside piece. We could just as well let it be 8x, but I suspect that I won't get very far that way. So actually, let me make a mistake here. Just to point out, it's fine. You're going to make mistakes, and I shouldn't say they're mistakes. They're attempts at doing a u substitution, and without the intuition that comes from doing these a lot, you're going to pick the wrong function to substitute for u, and that's fine. We just have to be willing to go back and pick a different u. So here I'd have 8 dx, but notice there's not really a way to get the 4x squared. So by the time I do my u substitution, I shouldn't have any more x's in my function. But I don't really have a good way to get that 8x squared. There might be some things I could do, but I'm going to try something else. So that u doesn't work. I'm going to try the inside of the cosine function. So notice, I've got, if that's my u, 4x squared plus 3, my du, I have it, 8x dx. So this 8x and this dx make up my du. That is all du. So the way this is going to look when I do my u substitution is I'm simply going to have cosine of u, and the 8x dx kind of gets wrapped up into the du. All right, and that's easy enough to integrate. It's just sine of u. And then back substitution, I simply have sine of 4x squared plus 3. And of course, I should squeeze this in here, that constant that tags along with us. Okay, so now let me try the next one. So here I'm going to let my u equal, and again, notice what's happening is I have an x to the third down here, and when I take the derivative of x to the third, I'll have an x to the second, which I have up here. So that's one of the things I'm looking for when I'm trying to decide what should my u function be. All right, then du is simply this, negative 12x squared dx. All right, now notice I don't have a negative 12x squared dx, but I do have a 2x squared dx. So what could I do to make sure this on the right side is a 2x squared dx? Well, I could divide both sides by negative 6. So that I substitute 2x squared dx with negative, let me put my negative up here, negative 1/6 du. So again, the reason I did that is this 2x squared dx is what I have. And I can substitute all that now with my negative 1/6 du. So what this looks like now is we're going to integrate 1 over square root of u times negative 1/6 du. And of course pull the negative 1/6 out, and this is really just negative 1/6 when we're integrating u to the negative 1/2 du. All right, and this is a fairly straightforward integration. Keep that negative 1/6 coming, add 1 to the exponent, and then divide by the new power 1/2, and you'll get a 2. And then don't forget to plus c it. All right, so ultimately this becomes 1/3 times my what I substituted for u, 1 minus 4x to the third to the 1/2, or square root that, and then plus c. Okay, so let's now try this one. This one's a little more interesting, although it doesn't look too interesting. It looks fairly simple. But if I try to integrate this with a u substitution, so we are integrating x over x minus 2 dx. Well, what should we try for our u? I'll give you a hint. U equals x never works. Now you're just replacing one variable with another. You could do it, it just never does anything for you. Du would equal dx. Okay, so the only other real possibility would be u equals x minus 2. All right, du equals dx. Now, that doesn't look like it's going to do a whole lot, but here's the trick. Because at this point, what we have is something over u, specifically x over u, and then du. But remember I said, once you do that u substitution, you shouldn't have any x's anymore. So, you got to do something about that. Well, what do? We don't have an x specifically in either the u or the du, so it doesn't get wrapped in either. However, we could do a little shift over here, add 2 to both sides, and we see that u plus 2 equals x. So we substitute that x with u plus 2. All right, and this is a little easier to deal with, because what can we do? We can split up this fraction over that plus. So we'll have integral of u over u du plus integral of 2 over u du. And this, of course, is just 1. So the integral of 1 du, that'll be u. And then this one is a constant multiple of 2 times the integral of 1 over u. And the integral of 1 over u is just the natural log of u. And then, of course, plus c. And finally, let's back sub the x minus 2 in, plus 2 ln x minus 2 plus c. And there's our integral of x over x minus 2. Okay, so now let's do this one before we get to some more, even more interesting stuff. This is the cosecant of 4x times the cotangent of 4x. And I should say cosecant squared, that's important. Cosecant squared or cotangent. So let me try that here. We're integrating cosecant squared of 4x cotangent of 4x. All right, so first thing you might try is u equals 4x, du then equals 4 dx, and so 1/4 du equals dx. So then we substitute those and you get cosecant of u, cotangent of u, and then du, and let me put that 1/4 out front because it's a constant multiple. But notice I'm still stuck with this cosecant squared and cotangent, and I just don't know off the top of my head how to integrate all that. So that's not working for me. Let me come back up here and try a different u sub. So how about u equals, well, now let me try to include one of these cosecants or cotangent functions. Well, we could go a couple different routes. If I were cosecant, notice my derivative is cosecant cotangent. Or if I used u to be cotangent, the derivative of cotangent is cosecant squared. So let's just pick one of those. Let's try cotan of x, rather 4x, huh? Then du is 4, because of the chain rule, cosecant squared 4x dx. All right, and of course we've already got this, so if we divide 4 to the other side, that's what we'll use for our substitution. Okay, so I'm going to substitute u in for cotangent, and I'm going to substitute cosecant squared dx in for du, and then I'll have to throw that 1/4 out front. So this is really 1/4 integral of u du. And now that becomes 1/4 u squared over 2, which is cotan squared of 4x over 8. All right, so there's some good examples on using the substitution method. Let me look at a few more examples that have something interesting in them. For example, this first one, x over the square root of x plus 1 takes it a little step further. So we're integrating just the difficulty a little, takes that a step further. X plus 1 dx. Now, I shouldn't put equal there yet because I'm not quite ready. I need to figure out a good u sub. And remember I said that u equals x is never going to help you. U equals, you might try u equals square root of x plus 1, but then notice du equals 1 over 2 root x plus 1. And we don't have this and this. So put a dx there. So we're not going to use that u substitution. So let's just try the only other possibility that I'm seeing, u equals x plus 1. And then using the trick that we did before, that means, so subtract 1 from both sides, x equals u minus 1. And du equals dx. So now we have all the pieces we need to substitute. We've got an x plus 1, we've got an x, and we've got a dx. All right, let's plug it in then and see what we get. So we're integrating u minus 1 over square root of u du. And now I can split that up into their own fractions. So this is integral of u over u. Let me call this u to the 1/2 instead of square root. And then minus, just because integrating is a little easier. And then minus the integral of 1 over u to the 1/2 du. Well, of course, this one, u over u to the 1/2 becomes u to the 1/2, and when you integrate that, that's going to be 2/3 u to the 3/2 minus, and then here we've got u to the negative 1/2. Add 1 to that, you're going to have 1/2. U to the 1/2 divided by 1/2, which is where I get the 2. All right, and then plus c. And then finally, we just have to back substitute what we had substituted to begin with. So this is 2/3 x plus 1 to the 3/2 minus 2 x plus 1 to the 1/2, and then plus our constant. Okay, now this one might look familiar. It does come from our hyperbolic trig functions, but I'm going to ignore that for a minute and just try to find a u substitution directly from one of these functions. So if you, well, let me rewrite it. E to the x plus e to the negative x over e to the x minus e to the negative x plus c. And I switched the plus and minus. So this is my plus and this is my minus on top. Okay. Well, again, don't use a u substitution of u equals x. So what's the other possibilities? U equals minus x, that's possible. I could try u equals this top function, or I could try u equals the bottom function. But notice, if u is the top function, du is going to be the bottom function. And if u is the bottom function, du is going to be the top function. So when you're in that situation and you have the choice, pick u to be the bottom function, because you need your du to not be in the denominator. Du has to be in the numerator. So u equals e to the x plus e to the negative x. That means du is e to the x minus, because of the chain rule, e to the negative x dx. All right, so really we are just integrating 1 over u du. I don't know where this plus c came from. That should have been a dx. Sorry about that. All right, so now integrate 1 over u. That's just simply ln of u plus c. And then finally back sub in. This is going to be ln of e to the x plus e to the negative x plus c. Just a quick side note, I dropped the absolute value because this is never negative, e to the x plus e to the negative x. All right. Now we had one more on this page, this guy. So that's x plus 1 and a square root of 3x plus 2. And that should be a dx. Now when trying to figure out what to u sub here, I might try x plus 1, du then is dx, but then I'm missing everything I need for the square root of 3x plus 2. Okay, so then I come back and I say, okay, let's try u equals 3x plus 2. Du equals 3 dx. But again, now I'm missing everything I need for that x plus 1. But, and this might have worked up here, I just like better to substitute my square root arguments with a u, just to make those a little easier. Can I do anything here to make this look like the x plus 1? Well, I could, for example, add 1 to both sides. And then I could divide by 3 on both sides. So that is 1/3 u plus 1 equals x plus 1. So now I have something to substitute for that guy, the x plus 1. So this substituting is going to be 1/3 u plus 1 square root u, or because I like dealing with fractional exponents better, at this point I'm going to get a u to the 1/2. And then don't forget, I'm forgetting, I don't have a 3 dx, so let me divide out by 3. That gives me 1/3 du equals dx. So really I should have a 1/3 here as well. So bring those 1/3 out. I've got 1/9, and let me do it this way. Now I'm going to integrate u to the 3/2. Let me actually say that I'm integrating here. 3 to the u to the 3/2 plus u to the 1/2 du. And so that's not too bad. I'm going to have 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus c. And then finally, let me just back sub in, but I'm going to leave it that way. Not worry about the simplification, because I think we've done enough. 2/5 3x plus 2 is what I substituted. 5/2, and then same thing over here, but it's with the 3/2. 3x plus 2 to the 3/2. And as always, don't forget the plus c. Okay, so the next item is very similar, but the idea is that now we're dealing with definite integrals. So to do the definite integral, remember we just have to find the antiderivative and then evaluate it at the end of our interval minus the evaluate at the beginning of our interval. So these are what we're calling the bounds of integration. And the only difference now when we're dealing with definite integrals as opposed to indefinite integrals as we were before, when we're using this substitution rule, we have to change our bounds based on our u substitution. So in other words, if I was integrating from a to b, now I have to plug a and b into that u function that we're substituting to get my new bounds of integration. So let's try it on here. If I want to integrate this, the first thing we have to do is do what we were doing before, actually integrate. So find a u substitution. So maybe I'll try u equals, looks like 9 plus t squared might be good. 9 plus t squared. That means du equals 2t dt. I have a t dt, so let me divide out by that 2. That just means 1/2 du is t dt. All right, but now what I need is to figure out what my new bounds of integration are. So u of 4 is 25, and u of 0 is 9. So that means my new integral goes from 9 to 25, and I have 1 over the square root of u du, and then not to forget about that 1/2, I'll throw that out front. All right, but now that means my integral is u to the, let's see, we had negative 1/2, so that's going to be 1/2 now, divided by 1/2 is going to give me a 2 out here, and then from 9 to 25. And I'll cancel those out, the 2's. So now I'm just plugging in 25 and 9, so I get 25 to the 1/2 minus 9 to the 1/2, and that's really just 5 minus 3, so that's 2. Now, let me give you an alternative to what we did. I had this 1 over u to the 1/2 du. Double check that that's what we ended up doing. 1 over square root of u du. We went from 9 to 25. Now let's say, I mean, this was pretty easy getting these new bounds of integration, but it's not always. I mean, it's never that hard, but sometimes it's just either annoying to calculate those, or you don't want to have a bunch of, maybe you've got some plus pi squareds minus sine of square root of something. So it's just ugly to carry it through. So what we could do instead is say, let's just use our bounds of integration as u of 4 and u of 0. So I'm going to say, I'm going to make this a little bigger. I'm going to say my bounds of integration, not actually figuring them out. I'm just saying, all right, u of 4 and u of 0, whatever those are. And then I go through, so knowing that my u substitution was 9 plus t squared, I'm going to go through and integrate this. This is 1/2, and I know that this is 2 u to the 1/2. I'm supposed to integrate that from u of 0 to u of 4, but I don't like that. I don't like having to figure out what those are. So I can leave them that way and then go back to t's. And when I do that, I go back to my original bounds of integration. 1/2. Oh, we can get rid of that, the 2's. So what I really have is 9 plus t squared and to the 1/2 power. So I just back substituted my t, and now I can go back to my original bounds of integration. And if you do that, now you'll see plugging in here, we've got 9 plus 4 squared to the 1/2 minus 9 plus 0 squared to the 1/2, and again you're going to get 5 minus 3, which is 2. So either way you want to do it, if you want to actually change your bounds of integration and just carry them through until the end, till you get your final answer, or if you want to just hold off on calculating what those new bounds are, and then get back into the original variable. You can do it either way. That's entirely up to you. Okay, let me go through this one really quick. Some more trig functions. Now this one, I know that the derivative of cosine has something to do with sine, specifically a negative sign. So that looks like an obvious substitution. And what I'll do is that second method, I won't actually do my conversions. So convert my bounds of integration. So we're going to let u be cosine of x dx, and then du will be negative sine of x dx, and I made a mistake here. I shouldn't have a dx on my u. The dx is on my du. But I don't have a negative sign, I have a sign, so let me divide both sides by negative. That means negative du equals sine of x dx. And there's my substitution. So here, I'll substitute with negative du. And cosine, I'm going to substitute with u. So what I'm integrating is, I'm going to pull that negative out front, and this is just 1 over u squared du. But my bounds of integration, I'm just going to say this is u of 0 and u of pi over 4. Now I can integrate. This is negative, well, let's see, u to the negative 2, add 1, and then divide by the new power gives me this. U of 0 is my u of 0, and u of pi over 4 are my bounds of integration. But now let me back sub some back into my x's, and I have this is 1 over cosine of x, and evaluate that from 0, the original bounds of integration, to pi over 4, and I'm going to get, well, let's see, that's cosine of pi over 4 is root 2 over 2, so 1 over that is 2 over root 2, or just root 2, minus, and then cosine of 0 is 1, so we'll have this over root 2 minus 1. Okay, let's try one more of these examples, but feel free to fast forward through this one if you feel like you've got it. All right, so in this example, we'll call this example 3. We're integrating from 0 to ln of 4, e to the x over 3 plus 2e to the x dx. All right, I feel like having this denominator, always a good thing to try, having that as my u could work. And if it doesn't, no big deal, we'll go back and try something else. So du here is going to be 2e to the x dx. I don't have that 2, so I'll divide that to the other side. We have 1/2 du equals e to the x dx. All right, now substitute in 1/2 du for here, u for the denominator, and then, and this time, maybe I will go ahead and substitute and get my new bounds of integration, and that just means I won't have to back sub into x's. I can stay in the u variable. So u of ln of 4 is 3 plus 2 e to the ln of 4, but e to the ln of 4 is just 4, so this is really 11. And my other integration, the other end is plugging 0 in. This is 3 plus 2e to the 0. Of course, that is going to be 5. So I'm integrating from not 0 anymore, 5 to 11 of 1 over u du. Oh, but I did miss, looks like I missed my 1/2, so let me bring that out here. So when I substituted dx, I should have had a 1/2 du. Sorry, when I substituted e to the x dx, I should have substituted with a 1/2 du. Okay, but now we know how to deal with this. This is 1/2 ln of u. And we're going to integrate that from 5 to 11. Not a problem. 1/2 ln of 11 minus ln of 5. Using some log trickery, I can call this 1/2 ln of 11 over 5, or even more log trickery. Any of these last three answers are going to work fine. I'm going to call this ln of the square root of 11 over 5. Okay. Couple big ideas that you're going to see in Calc 2 a lot. This is something, if you can get this now, you'll be in good shape with some of the other integration techniques that you're going to use. When we're trying to integrate sine squared, here's the problem. You try maybe u equals sine of x, but then when you do du, you're getting cosine of x, which you don't have anywhere in here. Sorry, cosine of x dx. You don't have anywhere in your original function. So we're kind of stuck. And then you start thinking, well, what about some trig identities? So then you might try integral of 1 minus cosine squared of x dx, and now substitute that. And I'm not sure what you sub here. You could try cosine squared of x, or cosine of x, but you run into the same problem. If you try u is cosine x, du is 2 cosine x sine x dx with a negative on it somewhere in there. So that you don't have. So we can't substitute all that stuff. All right, so we're running into all kinds of problems. Here's the trick. It is a trig identity, but specifically, it's the one that says that sine squared equals, it is 1 minus cosine of 2x over 2 dx. And if you remember your trig, this is your half angle formula. All right. So now the way you integrate that, I'm going to come down here and do it. Integral of 1 minus cosine of 2x over 2 dx. Well, this 2 is just a constant multiple, so first thing I like to do is pull that out. And we're going to integrate 1 minus cosine of 2x dx. Okay, well, now let's split our integral up over that negative sign, and that simplifies things a little bit. So this is 1/2, and let me make this big. We're going to have integral of 1 dx, which will just be x, minus the integral of cosine of 2x dx. All right, and now we can u sub this 2x. So notice we don't have to do anything for this integral. That's just going to be x. But on here, let's u sub 2x. And du is 2 dx, but we don't have a 2. We can say, all right, 1/2 du will substitute with dx. All right, so let's plug in what we know now. Integral of dx is just x minus, and now we have 1/2 integral cosine of u du. The integral of cosine is just sine. So we have 1/2 x minus 1/2 sine of u. And now plug that back in, plug in the substitution back so that we have all x's. And again, just to be sure that we got the right thing, the right answer, try to take the derivative of this and see if you get back up to what we started with. But the big idea is that when you have a sine squared and no cosine for your dx, then you have to do some half-angle formula trickery like this. So it'll be the same idea for this next one. I just have a definite integral here. So give that one a shot. And then the last one I'll go over is this guy. Looks harmless enough, but many of the problems that we try are going to look harmless, and specifically many of the integration problems you're going to try are going to look harmless, but there's always a trick to them. So if I'm trying to integrate secant of x, several things you might try. You know that secant is 1 over cosine, so integral of 1 over cosine of x dx. Well, not much we could do here from a u sub standpoint. You know, if we said u was cosine of x, we would need a negative sine of x, or at least a sine of x, in there somewhere, because that's what our du needs, but we don't have that. So what else could we try? I can't think of anything. So here's the way you do it, and this is one of those things you might just have to memorize. We're going to multiply by 1, but as always, it is a fancy one. It is secant of x plus tangent of x over the same thing. Secant of x plus tangent of x dx. All right, how does that help? Well, let me multiply secant of x to the top. So let me distribute. And we get secant squared of x plus secant of x tangent of x all over secant of x plus tangent of x dx. Okay, now I'm going to let my u be that denominator. That means du is, well, what's the derivative of secant of x? Derivative of secant x is secant x tan x, and then plus the derivative of tangent x, which is secant squared of x. And notice that is what I have on top here. So that whole thing, dx, gets wrapped up into my du, and I end up with simply integral of 1 over u du. So this becomes ln of secant x plus tan x. And then, of course, plus c. All right, that is an intro to the u substitution. You're going to get very good at this, but you might not be right now. So practice, 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 and we will include some of these questions on our final exam. All right, guys, it's been a good semester, sort of. This whole thing with us kind of disappearing into the online world has been kind of strange for me, but anyway, I enjoyed having everyone in the class. It was fun while it lasted, and then we moved online and it got weird. So hopefully it wasn't terrible for you guys, and you guys have a good fall semester, even though we're still online. you know, maybe you have a good next spring semester. So anyway, keep in touch even after the semester ends. I'd be glad to hear about how your Calc 2 is going. But for now, focus on our final, and I will see you guys hopefully another day.